Welcome back. So now let us start from the slurry pool linked power model. This has been best described by Stephen Model. You can see here that this is the slurry pool component. All the terminology, JB is a fraction of ball charge, RM mil effective radius, RI inner radius of the charge, L mil EGL. EGL is effective grinding length. Effective grinding length, very important, because the mil length is not the mil effective grinding length. This has been a misnomer in many places. People consider mil length as the mil effective length. No, effective grinding length is totally different. Effective grinding length is totally different because two things are important, and what is the effective diameter of the mill. So if we knock off or knock out the volume occupied by the liners in the mill from the mill shell, then we come to some sort of volume. Then if we try to comprehend that in the form of a cylinder, then it will be a virtual cylinder, and the diameter of that is the effective diameter. Is this definition clear? Is this definition clear? There is a mill shell, liners are there, take out the liners. Take out the liner, you can do it in the area basis also, take out the liner areas, right. Liner area taken out from the area of the cross section of the mill. So you will be landing with some other cross sectional area. Now you see what is the diameter of that cross sectional area. So that is the effective diameter, okay, and effective radius is half the effective diameter. And EGL, effective grinding length, is very important. If I draw a half section of the mill, let us say this is there and you know this length. People say effective length is the average of this length, average of this length and that length. This is wrong, that is not the effective length. Average of this length, this is the charge level top. So average of this length and that length is the effective length of the mill. This is not correct. You got to see one thing. So if this is the L shell, you will take the L shell, plus there is LE1 plus LE2, which is the equivalent length of one corner and the other corner, or the one cone and the other cone. Now what is that? You need to you have to calculate the volume of this. You have to calculate the volume of this. Okay. Now volume by the cross sectional area, because if you see, so this is the charge cross sectional area in this area, right. So this volume divided by this cross sectional area will give you some length, some virtual length, we call LE1. Similarly on this side it will be LE2. So this is the summation of this is EGL, effective grinding length. Many times I have seen a flange to flange length of 4 meter. People are considering 4 meter as the effective grinding length while doing the power calculation. It is not correct. And effective grinding length is a function of the charge loading as well. So higher the charge, suppose charge level goes here, right. So this volume will be more, again this volume will be more, so EGL will be more. So it is a function of the charge volume as well. It is a function of the angle of inclination of the mill heads plus the charge volume. Is it clear? Effective grinding length. So RM mill effective radius, inner radius, L is the mill EGL, everything is defined now. So all other Z is a parameter, it's a parameter, its value is this. So this parameter has been used in the semi-empirical model. Now the beauty of this model is this: people normally talk of this area, which is the only the charge, shoulder and toe, but it is talking about toe and pull. It is talking about toe and pull as well. So if you put 0 over here, if you put 0 over here, you go to a great discharge mill. If you put the proper values, then you land to the overflow mills. And if this angle is something different, where the pull is not full, maybe partial pull, then you are analyzing a case where slurry pulling is taking place in a mill and in a great discharge mill, and the mill is losing power, and reason for that. So this is the best model to link the slurry pull with the power, right? And you can see here PP is the pull density and PC is the composite charge density. When I say composite charge density, it is a rock and ball, rock, ball plus the slurry and water all put together. This is a composite, and here it is only the pull density is the only slurry. Now in the next slide you will see that. This is the PC, where U is more than 1. What is U? U is the ratio of the volume of slurry to the volume of static ball interstices. I have just told you in the first session that between the balls there are voids, right? So it is a void volume. It is a void volume, right, by slurry volume. Sorry, it is a other way. Slurry volume by void volume. It is a slurry volume by the void volume. Slurry volume by the void volume. This is known as U, or degree of filling. This is known as U, or the degree of filling. Okay? If I say U is 1, that means void volume equal to slurry volume. Then only U will be 1. If slurry volume is more, then the degree of filling will be more. Normally for an ideal great discharge mill, U should be equal to 1. U should be equal to 1, ideal case. And for an overflow mill, U is more. It can go up to 3, 2.5, 2.6, 3, it can go there. We will come to that. But for U greater than 1, this is the composite charge density. For U less than 1, this is the one where U is less than 1. That means void volume is more, and this is the slurry pool volume. You have the only solids to deal with, only slurry to deal with. There is no steel ball, nothing is coming there. Okay. You can see here L cylinder, length of the cylindrical part of the mill, specific gravity of solid, composite charge density, pool slurry density. U, S is a fraction of solids by volume. E is the porosity of grinding balls. I have said this is the percent solids, fractional critical speed, effective diameter. All the terminology has been explained. I hope you all know about the critical speed. Again I am asking this question. Is it clear to you all? I should not be facing a question on critical speed later on. I hope you all know it. Now normally the total mill power is equal to the net power. What is net power? This is the P net. This is a big formula. It can be placed in a spreadsheet. You can do a quick Excel programming on that. That is not a big deal. So this is the P net, but P net is the net power. That is the power required for the mill with the charge. Now what happens for the empty mill running? Now this is the empty mill running power, that is the power, no load power. This is the no load power. So, if you add the net power with the no load power, you come to the total power, the P gross, you come to the total power, right, you come to the total power. So, total power is required sometimes to evaluate the condition of the mill. Now, some questions those were asked, now you will be starting to get those answers over here, automatically you will get it. Toe angle with the mill speed, what happens? Toe angle, let us say this one, with certain mill speed it has got no effect, then it comes down, and as the load increases, that means as the charge volume increases, it is coming lower, lower, lower. Shoulder angle, what happens? Up to certain speed it is same, then it picks up, and as the load increases it goes up. So, that is the kind of variation you can expect with the toe angle and the shoulder angle with the mill speed. Clear? Now, it is a very interesting thing, because just now I said what is the fill, degree of fill U, it is a void volume. Now, if I say suppose you maintain U as 1, suppose you maintain U as 1, I say you maintain U as 1 and I give you some slurry volume. Okay. Now, what would be the ball charge volume? What would be the ball charge volume corresponding to that slurry volume, so that U is 1? It is very easy. U is 1 means void volume equal to slurry volume, and if the void volume I know the porosity of the charge is 0.4. So, if I divide that by 0.4, I get the ball charge volume. Is it clear? Is that clear? Porosity of the charge is 0.4, that is 40% of the charge is void. Now, it is very easy to change the U when you are doing an experiment in a laboratory. It is very easy to change the U, because you can put measured amount of slurry, because charge is known, void is known. Now, with the void is known, void volume is known. So, with respect to the void volume, you can go on increasing or decreasing, and thereby you can alter the U. But what happens to a running mill? Laboratory mill, very easy. What happens to a running mill? Running mill, how do you know what is U? So, this is the challenge which has baffled the engineers for a long time. After that, it is Dr. Rogers and Dr. Austin, they solved. So, dynamic degree of interstitial slurry filling in the ball mill can be computed from Austin-Rogers model based on the mass transfer. It is proposed like this. What is JT? JT is the ball charge fraction unto the Tronian level. It is not the actual ball charge up to the Tronian level. Which Tronian side? Discharge in Tronian level. J, actual ball charge fraction. NC, fractional critical speed. D, mill effective diameter, effective grinding length, specific gravity solids. Now, F is the solid flow rate in the mill, meter cube per hour. What do you mean by the solid flow rate of the mill, in the mill? Suppose I say that I am sending free feed at the rate of 200 tons per hour. This is the mass flow rate. So, if you divide it by the specific gravity, then you get the solid flow rate, okay, volume flow rate of the solid, meter cube per hour. So, then now this can be F equal to F, or this can be F equal to 1 plus R for closed circuit application. In a closed circuit application, what happens? The recirculation load comes back. You know what is closed circuit and open circuit? Is it known to everybody what is a closed circuit and open circuit operation? You know. In a closed circuit mill, the recirculation load from the classifier, either it can be a cyclone or screen, whatever it is, that comes back, or that is fed back to the mill, right. So, then that mill sees a total mass through it, it does not see only the fresh feed. So, it is F1 into 1 plus R for the closed circuit application, where F1 is the fresh feed, right. F1 is the fresh solid feed rate. Now, K, there is a factor called K. K is the viscosity correction coefficient. K is the viscosity correction coefficient. K equal to 1.3 for solids less than 37% volume by volume. Okay. So, if the solids stay, so between the 37 to 46 in this range, which is normally the range for milling, between 37 to 46, then this is the value of the viscosity correction coefficient. This is a tested value, this is an empirical model. So, but people are finding good results using it. Value of K may be unto 4.5 for percent solids volume by volume of 0.65. If volume by volume percent solids goes up, then this one shoots up, K shoots up to this value. So, this is a direct influence of viscosity on the creation of dynamic degree of interstitial filling, U, because as this is very important. If this is not known, you will not be able to assess what is going on in the mill. Dynamic degree of interstitial slurry fill, UD. Now, this is something we talked about, the effective diameter. You can see this line, virtual line, is the effective diameter, DE, and DS is the inside the sublining, the mill diameter. 2 into T, T is the thickness of the rubber backing or the sublining. 6 mm sublining is normally used to protect the shell. Then AL is the area of the lining. You knock it off, right, and then you find out the equivalent circle for that, that is DE, which is a circle like this, which is a virtual circle, it does not physically exist. And next question is the charge volume. We have been discussing about a charge volume, etc., this many percentage, that many percentage, but how do we know? Then this is the charge volume measurement, you know. CV is the charge volume, 1.13 minus 1.26 into DE by 2 plus A by DE. What is A? This is the from center to here. So, DE by 2 plus A. So, that means the free height by the total height within the effective diameter. If you do this, then you will get the percentage charge filling. Many a times when we go to the industry, when we go to the plants, ask the people, what is the charge volume in the mill? They will say, oh, charge volume is maybe 30%. Somebody says 36%. And I said, how do you know it is 36%? Have you measured it? No, we know. I know. You can't say I know. Have you measured it? Then when we measure, we find it normally that the mill is holding 27, 28%. And they are shouting for something different, which does not exist. Now, the effective charge volume for power modeling as per Bond's model, it is very important. There is something called charge volume and there is something called effective charge volume. Now, one of the guy in one of the plant, he came and told me charge volume is 36%. I said, can't be. We measured, we found it to be 30%. Okay? But when I simulated, I used the figure 36%. Then he pounded on me. He said, why the hell are you using 36%? You said that it is 30%. I said, two things are different. What is the difference? One is the only ball charge volume. Now, if I consider all the interstices in the ball are filled with slurry, then the same volume of charge will hold or will make higher weight. Will make higher weight, or because with 40% porosity there has to be some value of the weight. When porosity is nil, the weight will be more. Now, if you consider that more weight, if you divide that by the actual bulk density, then you will find the fill percentage has gone up, as if the charge has expanded. Sorry, you see here, expanded charge volume. Normally you see here that 0.3, normally 30% is the normal benchmarks, 30% actual volume. Now, for different slurry specific gravity, slurry loading or the volume by volume fraction, normally we operate here in this zone, and if I consider U as the normal filling, if you take, then you go there, you are coming in that region of 35%. So, as if your charge has expanded, and that is the charge you consider for modeling the power, because physically they got to lift that weight. Is it clear to all? Now, this is an interesting thing, the variation of the slurry pool with level of slurry filling. You can see here. Now, slurry filling 1.5, 2, 2.5, 3. Now, you see here, you are seeing that pool angle is decreasing. Then why I am saying pool is increasing? 105 degree, 135 degree. This is not the case. Case is like this. Let us say you are measuring from here. So, 105 will be here, 135 will be somewhere there. So, the level of pool corresponding to 135 is less than with 105. That is what it is. That is what it is. Apparently, it is a confusing. Now, this is the pool angle with the speed. Now, here you should not consider these two sets of data, because these are the wrong data. These are the wrong data, but a normal trend pattern is this, something like this. That means against any particular fill, if the speed goes up, then what happens? You see a rise in the curve. Rise in the curve means the slurry angle is increasing, 135, right? Slurry angle is increasing, and then increases, and then suddenly dipping down. Can you explain how it is happening? So, slurry angle going down means pool is rising. So, here slurry angle is going up, that means pool is falling. So, with the high speed you are generating high voids, right, dynamic voids. So, it is possible for the void to accommodate that and drag it quickly. That is the reason you are seeing this trend. But these two are the error in the experiment. So, it is showing something different. So, do not consider these two cases. Now, let us look at the power. What happens in the pool? If the slurry filling is 1, you get the highest power. I told you that for the great discharge mill, power drawn is maximum. Why? Because there is no pool. From the mechanistic model, we have seen that there is no pool, no lever arm for the slurry, nothing is creating any counter torque. So, the power drawn is maximum. So, corresponding to 1 at different speeds, but the trend, see the trend, power is the max, and then as the filling increases, power comes down. So, for overflow mill, you may be here, anywhere here, you may be anywhere here, okay. This is the trend. Now, the question is, this is understood, this is also understood, but why that? This is understood, this is also understood, but how do you justify this one? That means, when there was no pull, only the balls moving, the movement is not proper, right? When there is no slurry, as if there is no powder, no slurry, nothing, it's only the mill rotating, right? Dry, absolute dry. The charge motion is totally different. As you start putting in, so it is picking the some of the slurry and drawing it and dragging it into the interstices. So it is getting the enough lubrication to overcome the friction, right? So the charge can go up and up further, right? It is happening, and then at this condition, this is the best condition. So that is why power shoots up between 0 to 1 in the filling. So charge movement is impaired. These are the similar data, but only thing is this against different speeds. Same thing. Now this is another interesting thing, because there were some groups who were doing that experiment, and parallelly some other groups, they tried to do another observation. What is the influence of the mean density of the rotating charge? How does it behave with the filling? Does the charge mean density change, increases, decreases, what? You see here, the trend is similar, but trend is taking place close to 0.5, and for higher concentration, let us say close to 1. But since the experiment was conducted in a very small size mill, so you have got some sway in the data, but the trend is absolutely correct. So yes, we get this sort of filling, average filling. The trend is perfect. So when the mill draws power, the mean density of the rotating charge is very, very important in that power model. If that does this, so it is obvious the power will also do that. Now this is another interesting thing, effect of the slurry filling on the mesh of grind. What happens? Experiment is telling that if you fill high, that means if you operate with a high pull, then you will be grinding finer. If you operate with a low pull, you will be grinding coarser. It is a fallacy again. It should have been other way round. It should have been other way round. If you are having pull, then what is happening? Higher pull, what is happening? The pull is forcing the charge in a manner, when it is the charge avalanche is coming down, it is giving it a resistance in a manner so that the spinning of the charge is taking place in a higher scale, which is promoting the attrition grinding more, right? So you are getting this, but in this case it is not happening. So it is avalanche is landing sharply on the toe. It is coming, yes, it is a cascading mode, but it is approaching toe. Here, while approaching toe, another spin is created over there. Now people opined out of this from this result, they are very reluctant to see the other things. They say, well, for finer grinding we should use high pull, and for coarser grinding we should use low pull. See how the conclusions come easily. Can it happen? As I said, it is an energy process. It is an energy process. That means here the power drawn by the mill is less. Here the power drawn by the, if you can see here, 2 minutes grinding, 8 minutes grinding, 30 minutes grinding, these are batch grinding process. It is a batch grinding process in a laboratory, right? But the trend is more or less same. So that means there is no dynamic void fill over here. And number 2 is that as we have seen that with the change in the filling, that means as the filling percentage increases, then the power drops. So that means with this power there will be a drop of the power. So with the drop in the power, can I have fine grinding? Yes, I can. Yes, I can. If I maintain the same residence time. That is the fallacy. Here is the residence time. Here is the residence time. If I maintain the same residence time, but normally you cannot maintain the same residence time, because with this the high pull means low residence time. The fallacy is here, identical residence time. So somebody has done an experiment based on identical residence time and he is predicting a result based on the varying residence time. So this is wrong, concept is wrong.
I think the red one is finer size distribution.
No, red one is red.
Because they are smaller sizes.
Yeah, this is the smaller size, right? Passing this thing. Now this is with the fixed grinding time. And when we do in a mill, it is a variable grinding time. And what happens? It is on the other hand, I would say that wherever you are having the counter spin, you can have the finer particles. If you have a high pull with a high viscosity, then which promotes a spin additional, then you can have a finer grind, right? But not in terms of the whole energy. That is the problem, that if I say F80 in terms of P80 may not be the much of a difference, but the angle of the curve when dipping down will have some difference, some divergence. So that is the result out of this. But here these things are fixed. Now the manifestations of the problems associated with higher percent solids weight by weight in an overflow ball mill. What happens? What are the problems what we face? Either all or some of the below mentioned features appear as a sign of maloperation. Number 1, product size becomes coarser without any change in the grind input conditions. Suddenly you will find that cyclone is giving you the higher cut, coarser size in the overflow. But when you check, you find the downstream inputs, they have not altered. Now you will find ejection of the grits. Now here I define the grits like this: partially ground mineral, these are not fully ground, through the overflow discharge. Ejection of smaller size of grinding media along with the discharge slurry. Spillage to the feed end trunnion side of the mill. Minor drop in the mill power draft in spite of maintaining the required charge level in the mill. So this could be the manifestation of the problems, where we are playing with this. Okay. Now let us see. The effect of slurry rheology on the grind kinetics in an overflow ball mill. It has been again studied by Austin. If you see, this is the first order breakage constant and this is the critical 80% passing size. Now you see 20%, 30%. Now here in this area, the variation is going like this: 60% solids, it is like this. If you see here, 54% solids. If you look at here, again 60% solids. In this zone, 20% solids and 45% solids in this area. So breakage kinetics, it is changing like this and with the critical 80% passing size. Suppose I peg 80% passing size, a particular 80% passing size, and I see what happens with the change in the percent solids volume by volume. So nature is like this. So that means it is affecting the breakage parameter. It is affecting the breakage parameter. The closed value is here 54%. So, you can see breakage parameter has dropped. Let us see. This one is the one which has given more refinement to the earlier picture. It is telling the critical passing size has got a variation with the percent size volume, you see curve is here. So, from 40 to 45 is the operating percentage solids volume by volume for grinding, because under that condition this one stays finer. Then the moment you go up, this one starts going up. That means grinding rate is retarded both ways. If you go in this side, then also grinding rate is retarded and the size is coarser. If you go that way, then also it is coarser. So, you got to stay within a zone that is defined by 40 to 46, 45% solids volume by volume. So, this is the ideal operation or the operating zone for any overflow grinding.
This one is independent of feed characteristics.
Independent of feed characteristics. It is from the rheological point of view. It is a rheology which is impairing the breakage kinetics and which is in turn creating coarser product. Now, this is another interesting case. There is another thing which is called the free pool area. Now, you can see there the area beyond the trajectory borderline is the free pool area. Now, there was one case in USA where we went there and we found the similar things. When we saw and analyzed, you can see the square lifters, 90-degree phase angle, and how our lifter has got certain phase angle. So, in that case the trajectory was like this. So, virtually there was no free pool, and it is important that the velocity of slurry through the free pool should be less than 0.3 meter per second. If that happens, then your pool is functional, otherwise your pool is defunct, and the moment that happens, ejection starts. So, they were also getting grits and balls. So, we analyzed this one and we gave them this solution and the problem vanished. And why the problem? It is one problem is this. The second problem was they were running the mill at 74% solids weight by weight, which corresponded to 53% solids volume by volume. So, on one hand there was a problem in the coarse feed, on the other hand there is a problem with the trajectory and the free pool, and there is a problem in the rheology. All put together there is a exodus of your grits and balls. Now, in one of the plants in Africa, it so happened they wanted to push more, right? And in a closed, that mill was operating in a closed circuit. What happened? In that method, they just forgot to maintain the desired percent solids in the mill. So, the percent solids in the mill was in the tune of 74 for a gold or ball milling, right? 74% solids. And because of that, the rheology got changed, rheology impaired the grinding. So, they started first generating the coarse. Now, coarse is being reported to a cyclone, right? So, the cyclone recirculation load started increasing. So, it used to be a vicious circle. So, more feedback, more problem, because try to remember one thing, there was nothing in that plant to take care of the proper dilution of the cyclone slurry. Some designer has given them an idea that the slurry from the cyclone will come at 72% solids, you do not have to worry. So, you take care of the dilution for the fresh feed, but in the actual operation and under that condition it would be about 300% recirculation load, design criteria. But when we checked, we found that the recirculation load was 500%. So, there was no dilution facility available to control that. So, more and more and eventually the slurry lost mobility, mill seized, right. So, that was the condition, because people only looked at one thing, push more, that normally happens in the industry. because in the industry you will have your KPA, KRA, all these terms, terminology. Very soon you guys will be familiar with that. So you will be given a target, you got to fulfill it. Now, please, while trying to fulfill that, do it scientifically. Otherwise, this sort of things will happen. Now, the reason analysis. All the overflow mills operate with degree of slurry filling in the range of 1.8 to 2.5, leading to a well demonstrated pool. With higher volumetric percent solid loading beyond 46%, slurry viscosity in the pool goes up, exhibiting higher yield stress of the slurry against the same shear rate. Right? Due to the higher viscosity of the pool slurry, the same does not travel to the normal slurry shoulder position during the charge movement. Slurry has got a shoulder position, so it does not travel up to that with that shear. This leads to the drop in the breakage rate. Okay? As the grind kinetics is affected, grinding in the mill results in the generation of coarser product. Yes? Coarser output results in higher recirculation load back to the mill, operating in closed circuit with higher slurry density. This results in the following sequence of events. What? Further increase in mill pool solid loading, which eventually lead to substantial settlement of the solids in the pool bed in the form of muck or mud, with the process water staying at the top of the pool. This causes lowering of the pool CG point, leading to the increase in the resisting torque arm and some more drop in power. Because with the slurry pool, suspended slurry pool, the CG point will be somewhere. When they will have the settlement, the CG point will further go down. So, the counter torque or the resisting torque value will be more. So, the mill will start losing power. Okay. Higher recirculation of the mill would cause higher slurry volume through the free pool area, which is bad. A part of the settled pool solid paste with very high yield stress, behaving like Bingham plastic fluid, when pulled into the ball charge kidney during the charge motion, the same push back the smaller size of the media or any unground particles locked in the ball interstices towards the pool side during its return path. So, whatever would be forced in somehow, it will, the small particles and the small balls will get embedded there. On its return path, it will be carried to the pool area, pool side. Stuffs on their way to the pool would eventually go out of the mill by the movement of the axially advancing thicker slurry. Something is being pushed or the pulled in, and you have got a slurry motion there. So, that will take it out. That means you have got certain thing being pushed in this direction, and you have got a axial direction. So, that will be picked up, and is it clear? So, when the slurry is getting back to the pool with the embedded balls, right, or the grits, the paste part, it will come back, and you have got an advancing slurry also. So, which will wash it out, and it will go out of the mill. So, this is the phenomena. Now, what are the remedial actions? Percent solids by volume in the slurry in the overflow ball mill must be checked and maintained within 46%. Now, there is another important thing, dilution water addition amount at the feed end to be set accordingly, because now you will see that if I push more solids, there is a ratio controller aided flow meter, right, which guides the water accordingly to maintain the particular solid liquid ratio. So, that has to be set properly, so that the slurry density does not go beyond 46%. In a sack ball circuit or in a closed circuit ball mill, water addition point with a variable quantity range to be provided at the cyclone underflow box to ensure that cyclone underflow slurry reaches the mill with the same desired pulp density as the fresh feed. This is the problem, because you are getting maximum from the cyclone. If you get 1 from the fresh feed, you get 3 from the cyclone. So, you are taking the corrective action on 1, but you are not doing anything on 3. So, there has to be some action point on that area. So, in the form of a dilution water head. And ball charge trajectory in the mill should not be made aggressive by providing suitable face angle in the shell lifters to ensure that the effective free pool area in the mill becomes larger. So, if somebody can maintain these three, the ball mill should be working fine and they should not have any problem at all. Let us see a typical thing, typical mass balance. What we do, this is the ball mill working in a closed circuit, right. Now, this is the fresh feed, specific gravity, this is the feed rate tons per hour of liquid, meter cube per hour of slurry specific gravity, this is the percent solids. Okay. I said liquor we use 1.03 to 05, so you see here. And this is an important parameter. What is the CV? That is the percent solids volume by volume. I am telling 68%, but that is yielding 45.47. So, I should stay with 68% only, not to exceed that. So, that becomes a checkpoint immediately. Cyclone, it is coming like this with the 75% solids, which is not good. So, I need to do something here. If I do not have anything here, then in this I need to have a water addition point, so that I can reduce this one to this level. Okay. So, normally this is how the mass balance is done. That is it.